Welcome to Tempe Town Lake. It's a man-made lake in downtown Tempe, Arizona. It's quite well developed on both sides, so it's an urban ecosystem for sure. And we've been studying this lake since about 2005 with an interest in lake biogeochemistry, lake metabolism, and how the lake responds to press and pulse events, which could be everything from climate change to storms and floods. So I'm Hillary Hartnett. I'm a professor in the School of Earth and Space Exploration and the School of Molecular Sciences at Arizona State University. I'm a biogeochemist, and my lab's expertise is in carbon and nitrogen cycling. So we've been looking at dissolved organic carbon content and composition. This is my student, Donnie. He's a PhD student in the School of Molecular Sciences and part-time aquatic chemist on this project. He's in the process of setting up meters for our routine water quality measurements, which include pH, conductivity, dissolved oxygen, and a sample for dissolved organic carbon and carbon fluorescence, which we use to look at organic matter cycling and organic matter quality. We started this work in part to understand whether this urban lake has typical biogeochemical cycles and how productive it is. What we learned early on is that the lake is pretty dynamic. It has strong seasonal responses. It has big interannual variability based on temperature, rainfall, which is intermittent here in Tempe, Phoenix. And this lake occasionally acts like a river. They lower the dams, water flows through town, and when the flow is reduced, they put the dams back up. What that means from a chemistry standpoint is that the lake gets to relax back to its steady state conditions, and that gives us some idea of how quickly the lake responds to changes. Donnie is collecting a large volume water sample for dissolved organic carbon. We collect these as surface water samples, and we take them back to the lab, filter them, and measure carbon content by high temperature combustion and fluorescence characteristics of the dissolved organic matter. So this sample is happily going back to the lab. So one of the things we've learned about the lake, which is quite exciting, is that the carbon chemistry responds very differently to seasonal rainfall and inputs of water from runoff from the sides, right? Stuff that comes across the landscape, versus river flow, which brings carbon from a completely different source. And if you look closely, I'll try to zoom in, you can see that there's actually a ton of algae in the lake. The lake is highly productive, and we're interested in how oxygen production can be used to calculate lake metabolism. Lake metabolism allows us to look at whether or not the lake is inherently autotrophic, whether primary production exceeds respiration, or whether the lake is heterotrophic, with respiration exceeding primary production. We can't do that with our routine biweekly sampling, so we've added a new component to the lake measurements, which uses an in situ data sonde, and now I'm going to show you some pictures of the data sonde. So here's Donnie. Hi, Donnie. He's holding the data sonde. I'm going to zoom in on this a little bit. The data sonde is a Eureka manta, and the business end down here has multiple sensors, including oxygen, pH, conductivity. It measures depth and temperature, but it's also exciting. It has a chlorophyll A sensor and a fluorescence dissolved organic matter sensor. And so we're using this both to compare our lab data, but we can take measurements at 20-minute intervals, and that allows us to calculate whole lake metabolism based on diurnal oxygen cycling.
This is one of the accidental wetlands in the Salt River. We'll describe to you what we mean by accidental wetlands in just a moment. The Salt River was a perennial river for millennia until the late 30s, when the last of 7 reservoirs and dams upstream were completed. Now there's water in the Salt River only in a few places. That water generally tends to come from drainage from stormwater sheds in the city itself. The size of those stormwater sheds determine how much water is actually being put into the Salt River bed, and if enough water is coming in, we find these accidental wetlands developing on their own. They're completely undesigned, unmanaged, they are truly accidental. There's about 7 of these accidental wetland complexes throughout the metro area in the Salt River Basin, and we have been studying these systems for a number of years. Interestingly enough, a young coyote just ran out in front of us.
I'm Nancy Grimm. I'm a Regents professor here at Arizona State University in the School of Life Sciences. Now, my team's been studying these fascinating accidental wetlands for several years. These wetlands haven't always been here, however. Recent population growth and use of water that results in urban baseflow, plus changes in the stream channel owing to Tempe Town Lake, have expanded the wetlands over the last couple of decades. As Dan pointed out, whether the wetlands are ephemeral or perennial is a function of the size of the storm watersheds. And here you can see the storm watersheds in aqua and pink, very, very different sizes, really close to each other. Now, when we go down into the wetlands, I'm going to tell you about 3 main patch types that we've been using for studies of biogeochemistry. In the background, you see typha, that's one of the patch types. The foreground, you see Lowigia. Here's another photo of Lowigia in the foreground. And in the background, you see an open water patch, which is the 3rd patch type that we'll talk about. So let's go down into the wetlands and learn something about these fascinating systems.
Okay, so now we're down in one of the accidental wetlands. This is the wetland above Tempe Town Lake in Tempe. What's behind me is the affluent, or one of the outfalls, which includes treated affluent as well as urban baseflow coming in to this wetland area. So as you can imagine, given the sources, there's quite a lot of nutrient loading coming into these wetlands. And in addition, we also have found that particularly during high flow events, we get a lot of pathogens coming into the wetlands as well. So some of the work that we've done here within the wetlands is to look at the upstream, downstream changes in nutrients as well as pathogens. And this is work done by Monica Palta when she was a postdoc here, and she found that there was a really high potential for removal of nitrate and removal of pathogens in these wetlands.
Hi, I'm Marina Lauck. I'm a grad student in the Grimm Lab. And so when we're talking about different ways that nitrogen can be removed from the system, there's a couple of different pathways, one of which is denitrification, the byproduct of which is taking nitrogen from the stream and releasing it as N2 gas in the atmosphere. The other is DNRA. And Amanda Suki, a PhD student here at ASU, looked at how some of the dominant plant and cover types affected these processes, particularly looking at the 3 sort of dominant cover types being typha, Lowigia, and open patches. In this research, she found that Lowigia was the major driver for denitrification in these 3 different patch types.
So as Marina mentioned, the 2 major pathways of nitrate removal are denitrification and dissimilatory nitrate reduction to ammonia, where the nitrogen actually stays in the system. And so Amanda Suki, that was mentioned by Marina, as well as Amalia Handler, another graduate student, teamed up to measure the relative proportion of the nitrate removal that came from dissimilatory nitrate reduction to ammonium, DNRA, versus denitrification in these 3 patch types. And they found that it was predominantly denitrification, so that's a nitrate loss from the system. But they also found substantial DNRA in these ecosystems, and the substantial DNRA in the Lowigia patches as well. So This research is indicating that in these urban wetlands, we actually have a high potential for nitrate removal and for dissimilatory nitrate reduction to ammonium, as we have found in other areas. And the rates that they measured were rates that were much higher than other systems that have been reported.
As we walk down into the wetlands, we see evidence of people living there. Studies of the use of wetlands by people experiencing homelessness found that they use water in these wetlands for personal hygiene, that they prefer the solitude of the wetlands to homeless shelters, and that the microclimate of the wetlands is much cooler than the surrounding environment.